Welcome everybody to the Global Lecture Hall. Today we for the second lecture of this year's series. It's my pleasure to introduce, as you know, we have two main threads. A thread where we develop the basic idea about embodied AI, and this is Rolf and some other people. And while in the second half of the lecture, we have guest lectures. Today we have a guest lecture from Rory Glynn. I hope I pronounced correctly the name. And which you will see it will be extremely interesting because it will be a point of view on embodied AI from the perspective of an architect. I leave the floor to Rolf, which will talk about the title is of today's lecture is a theory of embodied intelligence, and the topic is what we are developing all along the series. So, what we mean as embodied intelligence. So, Rolf. It's my pleasure to introduce our mentor and founder of the Shanghai lecture, Rolf Fabio from Osaka today.
Okay, thanks very much, Fabio, for the introduction. I'm of course very happy to be here again and to see you all back in the global virtual lecture hall. So this is today again from Osaka University, just so you get the global picture. Here is China, here is Shanghai, where the whole endeavor started. And this is from Osaka, from a fish restaurant. And in the center, you can see Hiroshi Ishiguro. He is the crazy guy who builds the clones. And here are some very shy Japanese people sharing the fun with others. Okay, so here we go. Cognition as computation, successes as and failures, and the need for an embodied perspective on intelligence. So these were last week's topic. We were talking about the nature of intelligence, what it is, how it can be studied. Then we were discussing some issues of IQ, measuring intelligence, the Turing test, and the Chinese room. The three goals of artificial intelligence, synthetic methodology, and then we mentioned this idea of IQ and professional success. Now, the question is are there student presentations to,
yes, Rolf, this is He from Shanghai Jiaotong University. We have a...
Okay.
Yeah, okay. We have a student that will have some presentation. So, Nathan, can I share our screen?
Okay.
Yeah.
Just a moment.
Okay. So, right. Do I need to do something? No.
Okay, now you can share your screen in Shanghai.
We can see the screen now.
All the teachers and students in the virtual hall, good afternoon. My name is Cao Jing from Shanghai Jiaotong University. I'm very glad to deliver a short presentation about the Chinese room test. It is also known as the Chinese room argument. First, let's have a brief review of this problem. Can you hear? Can you see the video?
Yeah, we can see it.
声音放不出来。
怎么放？
声音放不出来，你就说。
But there is no sound from the video. We cannot hear the sound in the screen sharing.
Oh, sorry about that. It's a video. A Chinese speaker outside may think the speakers inside with instruction and characters that he can speak Chinese.
Do you want to comment on the video?
Sorry about the sound. Let's continue. The key of the Chinese room test is that someone can't speak Chinese is able to make others believe that he can speak Chinese. However, some people don't. And we continue. Actually, the virtual room, including the human and the instruction, can speak Chinese from the Turing's point of view. It can speak Chinese, but the human cannot without the instructions. And from another point of view, what if we have stronger instructions, like an encyclopedia or a dictionary, which contains every Chinese answer corresponding to the Chinese questions? And the virtual room, actually, some people think it just simulates someone can speak Chinese, but it didn't really thinking. Just like the models over there, certain questions input and certain answers output. How can we judge that the system inside the box is really thinking? And Chinese room test is not about language, but it is very famous because it proposed a doubt that whether it is possible to pass a Turing test without any kind of intelligence. And let me introduce Ian Gostman. It is a chatbot like Siri, which is the first chatbot to pass Turing test in 2014. Here is a typical conversation with the judges got, and this conversation is something very misleading. And this chatbot is designed not to behave like human in intellectual tasks, but it is designed to cheat the judges in a period of time. So is it also called some kind of intelligence? And finally, we put out the question how to define intelligence. Since this definition is ambiguous, so the Chinese room test can never draw a conclusion. And that's our discussion about Chinese room tests. Thank you.
Okay, thank you very much. So we have an idea about the Chinese room. There is, by the way, a whole literature about the Chinese room thought experiment. And I think it's a good idea if you just think about it yourselves, you know, the pros and cons of the argument. I guess one of the arguments of John Searle is that just judging intelligence on the basis of input-output behavior is simply not sufficient, right? But there must be something else, and it is never really clear what the something else is. Right, okay. So then we're going to have, this is about the IQ and professional success. Oh, I need to share my slides. I need to share my screen here. Okay. Share, and it works, yeah. So, right. So we will have a student presentation about IQ and professional success. So I'm going to skip the slides that actually pertain to this issue. So today's topics: classical approach, and then successes and failures, some problems, and then I will talk about embodiment and the famous, notorious frame of reference issue. So when did AI start? Well, it was in 1956. I mean, that's what people say, 1956, so it's almost 60 years ago. And there was a conference in the United States which was organized by John McCarthy, here in the lower right corner, and he was, I think at the time he was he at MIT or at Stanford University, I'm not sure, computer scientist. Then other participants in the conference were Noam Chomsky. Who is Noam Chomsky? I think he's a well-known linguist and political activist. In the meantime, professor at MIT who wrote this probably most quoted book in linguistics called Syntactic Structures. Then we have Herbert Simon Alan Newell with the logic theorist. And we have George Miller, a psychologist, who wrote this super famous paper, The Magical Number 7 plus or minus 2. Okay, let me just briefly comment on some of them. So Newell and Simon, they are considered the fathers of artificial intelligence, and they're always modest, and they made basically a program that could prove theorems in propositional calculus. Propositional calculus is the simplest form of logic that is known, and they had a sort of a recursive program that today a first-year computer science student can write, and they said this is the first time in the history of mankind that we have a thinking machine. So basically, to Newell and Simon, this recursive program that could prove theorems in propositional logic was thinking. Another, I think, really interesting idea at this conference was from George Miller, famous psychologist, magical number 7 plus or minus 2. So the idea is there's something called short-term memory, right? We all sort of have an idea of what short-term memory is, and George Miller asked, well, what is the capacity of short-term memory? And then he found that, I mean, how do you measure capacity of a memory? What, anyone here, maybe locally, how do you measure capacity of a memory? It's too obvious, the question is too simple, right? Yeah, bits and bytes, right, exactly. And so he wanted to sort of figure out what the capacity of short-term memory is, but then there seems to be wide variation, and it's not really measurable in bits and bytes. And so when you, for example, maybe an old-fashioned example, when you try to remember a phone number, you have an international access code, which is sometimes 00, and sometimes it's a 001 or something like that. And then you have a country code, which is 86 or 81. And then you have, maybe if it's a land-based line, you have an area code, and then you have the phone number itself. And you can actually remember very long phone numbers by this method of chunking up the phone number into pieces, or what George Miller called chunks. And then he said, well, it's not bits and bytes that you store in short-term memory, but it's chunks. And so we said, well, roughly speaking, it's 7 plus or minus 2 chunks that you actually store there. And if you think about it, you can have many examples also. You take language, you need short-term memory for language, then seems to be kind of a fairly good estimate of that. So it's not bits and bytes, but it's chunks. So I think it's a very interesting concept. And then finally we have Noam Chomsky, a famous linguist with his syntactic structures. And he basically has, maybe you know about his transformational grammars, so he was trying to come up with some grammatical structures for language, or computational structures for language we can discuss at a later point. I think he is completely misunderstanding the frame of reference problem, but we can come back to that later on. I'm sure Fabio Bonsignorio has something to say about that. Okay, now, what the artificial intelligence paradigm, also called the classical paradigm, is about. This is physical symbol systems hypothesis. And it's about the idea. So the argument is that intelligence is located at the level of abstract symbol manipulation. So you make a deliberate abstraction from the physical implementation. And the physical implementation does not matter. It can be electronic chips, flip-flops in a computer, or it can be spike trains in a biological brain, or it can be mechanical, as you can see down here on the right, or, as Hilary Putnam, an American philosopher, put it, it could be Swiss cheese. So Swiss cheese, of course, as a Swiss, I'm very happy that Swiss cheese could also qualify as an implementation of an abstract symbol manipulation system. And of course that's extremely powerful, because it actually means, that the kind of implementation doesn't matter. We don't need to worry about whether or in what kind of computer system, for example, this is implemented. It's a very powerful notion. Now, the idea is, of the physical symbol systems hypothesis, is that you have this is the real world. This is basically the real world, and then you have a representation. So it's the notion of a representation. And here you have a table, you have block A and B, and this is how you can represent it: block A, block B, table A, on B, A, or something of this sort, and then you have a hand that moves block B to the table. So you have a move operator, and then here you have an encode operator that encodes the real world situation in symbolic form. Here again, for the movement, for the action, you have an encode operator, and then here you get the result in the symbolic representation, you decode it, and then you should get the same result as you get in the real world. That's what you call a representation. Okay? So basically, intelligence equals manipulation on abstract symbolic representations. And this is also called GoFi. What does GoFi mean? Does anyone know what GoFi means? GoFi, good old-fashioned artificial intelligence. This is a term from the American philosopher John Hogland. And this is typically what we, when we refer to GoFi, we mean this computational abstract symbol manipulation approach. Here are just some of the research areas from the classical approach. We're not going to say too much about that, because we look more at natural forms of intelligence rather than these abstract symbol manipulation forms of intelligence. So we have abstract problem solving, knowledge representation, as we just saw. Then how you can act logically, we deal with uncertain knowledge, and so on, learning and memory, whatever. So this is adapted from a famous textbook in artificial intelligence, Russell Norvig. Peter Norvig is also together, is also responsible for the idea of these MOOCs, the massively online learning systems. Okay, let's look at some of the successes and failures. So this classical approach has had many successes. I mean, you can look at search engines, chess, we know that. Let's see, maybe I have some slides. Yes, chess. That was in New York, 1997 already, when IBM's computer Deep Blue won the world championship, a tournament against Garry Kasparov, who was the world champion at the time. In the meantime, we have chess programs that win against anyone on the planet. So I think this is a huge success for the classical approach of artificial intelligence is basically also what we call the brute force approach. So you just try as many situations as you can, and the deeper, the more moves ahead you can actually plan or test, the better you are going to play chess. Now you can see immediately why this is called the brute force approach, because it is playing chess, yes, but it's playing chess in a completely different way from human beings. Human beings work much more on the basis of patterns that they see and the organization of memory rather than this brute force search approach. Okay, manufacturing, big data, of course, is a huge success, and this idea of deep learning that now there's a real, I mean, big data and deep learning is a real hype, and we can discuss about this hype at some point maybe. Hypes always have a grain of truth, but then in the end they are hypes. At the failure side is, if you are interested in more natural forms of intelligence, in forms of intelligence in the real world, you know, like perception, manipulation, movement, common sense, and so on, then this approach has not been very successful. Anything that is to do with the interaction with the real world. So, okay, let me now briefly comment on this. If you have a virtual environment or a highly constrained artificial environment, you have high predictability, high programmability. So basically, you can, in an industrial environment, you can program anything ahead of time. And so this is a very, let's say, computational thing, because you know you have all the information about, the environment. By contrast, on the other side, in the real world, you have low predictability. You know, it's very hard to anticipate later on. I mean, if you're thinking about, well, you guys, most of you, or at least some of you, have a morning. So you're not thinking about drinks yet here in Japan. You know, it's already, almost 5 o'clock, so we can start thinking about having a drink later on. You're not going to plan the individual steps that you are going to take. That would be impossible and a silly thing to do. I mean, you just go there and then you react to the environment. That's a completely different situation from an industrial environment in which you can anticipate everything. Also, what's interesting is here, I cannot show it like that. Industrial environments, here, they are built, industrial robots are built of hard materials, electrical motors, you know, steel, hard plastics, and that works very well. However, humans, there's an interesting number, humans are built 85% out of soft materials. Now, the enormous power and the enormous flexibility of the human sensory motor system is largely due to the fact that we are built 85% of soft materials. So, what's the conclusion? The conclusion is that if we ever want to build robots that have the performance of the human sensory motor system, we need to deal with soft materials. And this is why we now have this big field of soft robotics. We need to understand how to deal with soft materials. It's completely different from classical control theory. We can come back to that point later. Now, if you are trying, now there are some methods from control theory that work very well in an industrial environment. They work perfectly. If you now take the methods that work perfectly in the industrial environment and you put them onto systems that should interact with human beings in the real world, I mean, this is kind of over here on the left, it's kind of a virtual world or a very controlled world, and here is the real world. If you put it on systems in the real world, this is what you're getting. So let's take the example of natural walking. Nathan, I have now 3 videos. Could you play them maybe in this sequence? Okay, this is Miriam, a former PhD student in our lab, walking very naturally. These are just very short video clips. Also, humans walking very naturally, and now we get the Honda Azubal, which of course is a very sophisticated robot, but watch how it walks. Maybe, it's not so important to have the sound, but you can see, it walks clean. It has this typical kind of robot walking gait. Okay, I think that's enough now. Thank you. It has this typical robot-like walking gait. Now, if by contrast you look at this robot, which is called the passive dynamic walker, it doesn't have sensors, it doesn't have motors, it doesn't have microprocessors, nothing, it's just a passive mechanical structure. And Nathan, can you play the passive dynamic walker? Ah, yeah, here we can see it. So it walks on an incline. It's a funny construction. Could you play it again, Nathan? Just once more. Yeah, thank you. Watch closely. It's got the arms attached to the hips. It's got these wide feet. But it has a certain sense of naturalness to its walking. And that is, let's say, broadly speaking, because it's exploiting embodiment. So let me just briefly explain natural walking. The reason we find it natural is because in human walking there is also a passive component. So when you're walking, you stand, let's say, on the right leg, the left leg is behind, and then the left leg has to come forward. So what the brain does is not control, as in a classical robot, the joints in detail, but it's controlling the body posture, and then the leg becomes like a pendulum, so we let gravity work for us, and then the leg swings forward. I mean, of course, muscles still are at work, but there is this passive component. And then when the leg swings forward, the tension in the muscles is relatively low and it's higher on impact. So what the brain does, it dynamically changes the muscle tension depending on what the legs need to do. So more generally speaking, the brain is dynamically changing the material properties of the system. And then, low tension when it swings forward, high tension when on impact. And so the brain it's as if the brain were delegating some of the functionality of coping with impact, which is a very difficult one, by the way, in robotics, to the material properties of the muscle tendon system. I think it's a very ingenious way of exploiting embodiment. Now, short question to the audience. Where is the memory for walking in this robot? Where is this ability for walking stored in the robot? Anyone? Would anyone venture?
Mechanics.
Mechanics. In the mechanical structure? Yes, in the mechanical structure, in the weight distribution, the length of the limbs, the frictional characteristics and the shape of the feet, and so on and so forth. Right? It's not in a particular location in the brain of the robot. I mean, of course, there's no brain. There's also no microprocessor. Normally, we think of memory as putting something in a particular location from where it is later on retrieved. This is a completely different notion of memory distributed throughout the entire organism. And maybe later we have the opportunity to talk about human memory. And in human memory, embodiment plays a crucial role. It's an underestimated role. People don't think about it like that. But keep that in mind for later. Okay, some problems with the classical approach. First question, why is perception hard? Why? And I need a physical object. Let me see. Yeah. Okay. This is a marker. I don't know whether you can see this. It's a marker. Okay. Now, if I hold the marker here, I have a certain image on the retina, which is called the proximal image, but that's a detail. I hold it like this. I have a certain image on the retina. If I hold it like this, I also have a certain image on the retina, but it's completely different from the previous one. And if I hold it like that, the image is even more different and has absolutely no relation to the image before, but it's always one and the same object. Makes it very difficult, makes perception very difficult. You cannot simply put a camera somewhere and then add a pattern matching program and then a database and then you map the pixels onto the internal representation. It just doesn't work. That's not how perception works. And the methodology, by perception, of course, we would like to have a system that can recognize objects, can recognize faces in a crowd, whatever. We need to build a system that can do that. Then we immediately see that just adding a camera and having a pattern recognition mechanism just doesn't work. Right? Okay, so it's a hard problem. So the computational approach has not been very successful at actually solving this problem. There are some approaches which we will go into maybe later on called active vision that try to mimic more biological aspects of perception. But let's look at some, for the time being, at some of the other fundamental problems of the classical approach. I think anything to do with the real-world interaction, real worlds, virtual worlds, has not been solved. I mean, we know how to build software, right? We know how to write programs. That's typically the easy part. The difficult part is where it comes to the interaction with the real world. That's the messy stuff. Right? But that's what natural forms of intelligence are about. Okay, let's quickly look at virtual world, real world. We talked about chess before. The world of chess is a virtual world. What does that mean? I have precisely defined board positions, and a board position either is this position or not. There's no in between. And then for each position, there is a finite number of possible moves, and all the player can do is select one of these possible moves. And then, if no move is being made, nothing happens. In contrast, if you go to the real world, now here's a soccer game, on the right you can see the soccer game. You don't have the clearly defined world. I mean, what are the possible actions of a soccer player, of a football player? What are the possible actions? I mean, basically, he can scream, he can sing a song, he can run, he can also kick the ball. He can do anything he likes. He can lie on the grass. So it's basically infinitely many things that he can do. It's a very different situation from the virtual world. And so we can look at some of the differences, but I think I have to go through this quickly. I have some examples here. In the real world, and that holds for any system, no matter how fast, information acquisition takes time. Because you have, at the minute you have a physical system, things require time. Right? There's no instantaneous thing. We only have limited information available. I mean, for example, we don't know what's going on in downtown Osaka now. But we really don't care, right? It doesn't matter. But somehow we know that it's not relevant for us here, what's happening in downtown Osaka, right? Physical devices are always subject to noise and malfunction. Always. I mean, even if, the salesperson tells you, well, this is the perfect sensor, it is subject to malfunction. It is subject to noise. There is no noise situation in the real world. You don't have clearly defined discrete states. Agents in the real world always have to do several things, not only one thing. A chess program only does one thing. It plays chess. But an agent in the real world, a human being, we have to walk, we have to talk, we have to breathe, we have to eat, we have to, move. look around, whatever. So we have to do many things, and the real world has its own dynamics, which means things happen even if I don't do anything. I mean, if I just stop talking and sit down, then people will start leaving the lecture halls, right? So I don't do anything, but things are happening. Also, the cars in downtown Osaka, they are still moving around even if I don't do anything. So the real world, in contrast to the game of chess, has its own dynamics. In chess, nothing happens if none of the players make a move. And then the last point, which is a really tough one, is that everything is non-linear, and that's why we always have in the real world very, very limited predictability. And this is why Herbert Simon then said, because of all these limitations, we cannot act purely rationally, but we're always acting on the basis of limited rationality, which he called the concept of bounded rationality. Okay, let's now look at three fundamental problems of the classical approach. First, remember I said, in this view, intelligence equals abstract symbol manipulation. There is this symbol grounding problem. Let's have a look. So this is a cartoonist Gary Larson, and he did a lot about cognitive science. This one I like very much. The trouble here is the real world doesn't come with labels. Now, if I look at a house, how do I know that this is a house, that I can give this the label house? It doesn't stand there. This is a shirt or a tree. That's perception. So I basically have to map what I see in the real world onto internal symbols. So the symbols somehow have to be grounded in the interaction with the real world, right? How's that done? That's the hard part about perception. How can I do that? And the computational approach has not been very successful at solving this problem. A really nasty problem is the so-called frame problem. And there's a literature about the frame problem, but I think the essence is the following. It's about models. And whenever you have a model, here's a very stupid model of a table with 2 blocks and not very interesting. But whenever you have a model of the real world, the issue is how do you keep the model in tune with the real world, because the real world continuously changes. And we all know that from navigation systems. You have a traffic jam somewhere, right? Well, you don't know, the navigation system does not know about the traffic jam unless someone or some system is updating the information in the model to say, well, there is a traffic jam there, okay? And the more detailed your model of the environment, the more difficult it is and the more effort you have to put into updating the model. Okay? So, there's an issue. Do you really want a model that is very, very, very detailed? And then we know that information acquisition takes time. You have to update more, takes more time, and then the model is much more likely to be inaccurate. And so this is called the frame problem. And one of the points is also most changes in the real world are irrelevant for what you're currently doing. The cars in downtown Osaka, we really don't care what they're doing. Because it's totally irrelevant to our lecture here now. But if you have a computer model, how do you know which changes in the real world are relevant and which changes are not relevant? Right? Tough, very tough issue. There is a beautiful example. I'm not going to go through it. I just want to mention it. Daniel Dennett, an American philosopher who did a lot of work, a very excellent work on philosophy of mind, came up with this robot example. And please go through it over the weekend, because over the weekend you typically don't know what to do. And then I think some interesting reading will be good for you. So I have all the information on the slides that we will upload to the web page. Yeah, have a look at that. Okay, so we need an embodied approach. Here are the two views of intelligence, the classical one, or the GoFi approach, good old-fashioned artificial intelligence, cognition, or intelligence as computation, and the other one that we will talk more about is cognition as emergent from sensory motor and interaction processes. Okay, so we looked at some of the failures. I mean, they were just not, the classical approach was just not very good at modeling perception, for example. And we looked at some of the fundamental problems, and then we have a beautiful quote by Louis Wolpert, not Danny Wolpert, there are several Wolperts. Why do plants not have brains? I don't know whether you've thought about this, why plants don't have brains. And then he says, well, the answer is actually quite simple. They don't have to move. So in this view, the evolutionary selectionist pressure on the development of the nervous system or the brain comes from the need to move, to locomote, to move around, and to orient in space, to interact with the real world, to survive in the real world. So in this view also, I mean, this is a nice evolutionary perspective on the development of intelligence. And what's also interesting here is that the brain is always part of a complete organism. You know, there's no algorithm or algorithmic ether somewhere out there where I can run algorithms. There's always a brain, and that's embedded into a physical organism. And the only way the brain, what the brain is doing, the information processing of the brain, can communicate with the outside world is through its body. That's the only way. And basically what the body experiences in the interaction with the real world is the raw material for the brain to process and to learn something about the environment. We come back to this point later on. So the interaction with the environment is always mediated by the body, and the brain is part of a complete organism. Okay, now I think to finish my presentation, the notorious frame of reference problem is one of my favorite problems. If you don't, I mean, you can forget everything we say in this lecture series, but don't forget the frame of reference problem, okay? I think it's absolutely fundamental, and I would like to ask Nathan to play the Hyder and Simmel video. It's about, I think, 50 or 60 years ago, two psychologists, they made this beautiful, at the time it was a movie, they didn't have videos, this beautiful movie. Just watch it, and then I will ask you what this movie is about. Okay, can you play the video now, Tom? Yeah, okay. Can you have a bit of sound? Okay, thank you very much. So maybe question to the audience, to the global lecture hall. What did you see in the movie? Anyone venturing an answer? Okay, maybe I can give an answer. I saw triangles and circles or discs moving around. You think it's a very good answer? What did you see?
Sure. I mean, I can comment on it. I can say that it was very influential in a lot of the thinking that I've had in the last couple of years. But I think the most interesting thing about it is just that people will irresistibly infer motion into those characters, those simple objects, and quite often they interviewed a group of people, and almost universally they told a very similar story about two triangles seeming to get into a bit of a fight over a circle. Some people think of it as a bit of a kind of love story. In that, the series of movements, people have recognized behaviors like aggressive behaviors, they recognize fear, joy. So it's also interesting that it's not done by animators, it's done by visual perceptual psychologists. But yet, even though it's not done by craftsmen of the trade of animation, it's still so easy to conjure life into simple objects just by the way that they move in relation to each other. So it's fascinating.
Okay, well, thanks very much, Rory. That's exactly the point, and I think what's important is that this story, these characters, we try to project our own feelings, our own ideas into these characters, but it's in our heads or in our system, in our minds, rather than in the minds of these triangles. I mean, these triangles, they don't have minds, they're just basically things, that are moving around. That's an aspect of the frame of reference problem. Okay, we've had the comment. Let me just give a famous example of frame of reference Simon's Ant on the Beach. Herbert Simon, the same Herbert Simon that we saw before, who claimed to have built the first thinking machine in the history of mankind. But he has a very beautiful book that I can really recommend. It's called The Sciences of the Artificial. And he says, okay, let's assume we have a beach and an ant, and there is some food and there is a nest. And let's assume that the ant has found some food and brings the food back to the nest. Now, what you see here is a very complex, winded trajectory. So it looks very complex. But the fact that it looks complex does not imply that the mechanisms by which it comes about also have to be complex. Maybe it's just very simple behavioral rules. For example, obstacle on the left, turn right, obstacle on right, turn left, otherwise go straight. And then you get this trajectory in the interaction with the real world. So the complexity is in the interaction. It's not in the brain. It's also not in the environment. It's in the interaction. Let's make a thought experiment. Let's just increase the body of the ant by a factor of 1,000. We leave everything the same. The environment is the same. The behavioral rules, or the brain, or the control is exactly the same. And then we let the ant run again. What's the new path look like of the giant ant with the same behavioral rules in exactly the same environment? Straight lines, more or less going to be a straight line like this, plus minus, right? Why? Because what were obstacles before are no longer obstacles. Even though, I mean, this is for a computer scientist, the environment is the same, the program is the same, but the behavior is completely different. This shows you that just looking at the program or just looking at the brain doesn't tell you anything about the behavior unless you know how the brain is embedded into the physical system and unless you know about the environment. I think it's a very, very important point to get across. So, 3 issues here. 1, a perspectives issue. Am I talking about the mechanisms of the end? Or trials? Or am I talking about what's happening in my mind? Then the behavior versus mechanism. Behavior always needs to be distinguished from the underlying mechanism. Behavior is interaction with the real world. The underlying mechanism is the control. Okay? Confusing the philosophers always have nice terms that you can use at cocktail parties. They call this a category error. So if you confuse the behavior with the underlying mechanism, that's a category error. And then we have a complexity issue that we already mentioned, complex behavior, simple mechanisms. Now, I don't know whether Fabio, we used to have a competition frame of reference because I said, it's really, really important. Now, if you discover that during one of the lectures the frame of reference problem is not mentioned, or I don't mention the frame of reference.
Yeah, I think we are going to repeat the competition. Yeah, I agree with you. Well,
very good. So either champagne, or for those who don't like booze, they can have chocolate or maybe Italian chocolate. I don't know. I don't know what you guys eat.
Maybe still, my doubt is about the price. Maybe we may still send Swiss chocolate or Cantucci, biscuits from
Okay,
Tuscany.
Cantucci is also okay. Yeah, it's very good. Okay, so I think that's all I had to say for today. So back to Fabio. Thanks very much.
Okay, thank you very much. Okay, so I think we may have a 5 minutes break, and then I will introduce the guest lecturer, today's guest lecturer, Rory Green from the University College in London.
What about the student presentations?
The student presentation, if they are ready, we may have it now from Moscow. No? Are you ready, Moscow?
Yes, I am ready.
Okay, so let's go for the student presentation.
My name is Alevita Nalmadian. I would like to tell you what do I think about IQ and professional success. I suppose that IQ level and professional success are not interconnected between each other. It can be confirmed by the fact that the basis of prosperity is not only about the intelligence. Your IQ, which stands for Intelligence Quotient, is a scientific assessment of your intelligence derived from standardized tests that measure problem-solving abilities, spatial imagery, memory, and general knowledge. That's a lot, but unfortunately not enough. And in my own opinion, the most important components of success are persistence, purpose, determination, and ability to concentrate on the targets. You are supposed to be a goal digger to achieve a success. If you rely only on your own IQ level, it means you don't know any better and you will likely fail. This strategy is a dead end. You can't capture the essence of what is a real professionalism in such case. The professionalism includes lots of the features. For example, showing up on time, staying on task, keeping the personal and professional life separate, giving other people respect, taking on extra assignments, listening carefully, and keeping the skills up to date, and so on. So as you see, the special entry and Bayesian term are add like a stroke and cheese. History notes more than enough cases when people with unsatisfactory IQ level became really successful and gained the recognition and respect of society. Such examples are Henry Ford, John Davison Rockefeller, Walt Disney, Michael Sowell, L.G. Fong, Tiger Woods, Alfonso Pinot, and so on. Actually, George Herbert Walker Bush's IQ level is 98, and that is lower than the level of a random American worker, and his son's level is about 80, what's lower than Britney Spears' results. There is also such a concept which is called AQ, emotional intelligence. It is an ability to tap into emotions and use them to make the life better. Being in touch with the feelings allows to manage stress levels and communicate effectively with other people, two skills that enhance the life both personally and professionally. Researchers consider that AQ is a fundamental part of success. IQ measures the level of cognitive intelligence, but there is also a social one, which is incomparably more important. Too high IQ level is typical for people with mediocre communication skills. They are usually introverts, with all the inherent limitations of introverts. By the way, widely used standard IQ tests do not correctly reflect the level of intellectual abilities, because they depend on the number of different subsystems of the brain. This conclusion was made by British and Canadian scientists on the basis of large-scale experiment with the participation of more than 100,000 volunteers. They came to the conclusion that the intelligence as a single essence does not exist. There is just a set of independent and different types of mental abilities.
Hello?
Maybe this.
Okay, great. Well, we are sorry for the delay, and now we have also prepared for the Chinese room topic. Which one? Mm-hmm. How do I play it?
Yeah, play the slide.
How do I play it?
Okay. Nathan will play. Okay.
All right.
Go ahead.
I am Steve, and if you can still remember me, I was the one who introduced our school last time. And can we please switch to the next slide? All right, thank you. So last week, we had a little discussion of what is intelligence, and just like the whole academic field and the industrial world, we failed because we can't define what is an intelligence. And Turing, and so we take an alternative, right? Mm-hmm. Turing took an alternative that something, and we don't need to identify what intelligence really is. We just need to find a machine, and if the machine can make a real human believe that the machine is a human, then we say that the machine is an artificial intelligence. And based on this, Turing designed a test, and it is shown on a diagram that was drawn by myself. However, there were people who opposed this test, and one of them was John Searle. And the next slide, please. All right, thank you. The Chinese room test is basically a variant of the Turing test. We can see all the same concepts here. There's an evaluator who doesn't know which one, who doesn't know who exactly in the room is, and the evaluator and the machine or person inside communicate through text, and the evaluator judges whether the replier inside the room is a human or a robot by the replies. And the Chinese room experiment shows that actually, if the machine even cannot really understand what the evaluator is talking to him, his reply or its reply can still cheat the evaluator into believing that the machine is a human. So Searle was basically using the Turing's test methods, but ended up proving that Turing's test was flawed, and that was something good we all agree on, because by debate we promote the by debating we promote the advantage of science and also all other kinds of fields, but we also have problems of our own. We question the Chinese room test too. And the next slide, please. And we believe that the Chinese test itself also has some limitations, as shown in the next slide. The next one, please. Right. Oh no. All right. So the first thing is that the Chinese room shows a machine can cheat in the test, but we don't really think that the cheating is the only way to make the evaluator believe that the machine is human. I mean, maybe there is really another way to win fair and square and make the evaluator believe to pass the Chinese room test. It's the method, the Turing's test method may be flawed, but maybe there's another way that we can build a strong AI, which was a concept that Professor Searle put up. And another really controversial thing, another complex topic is that what if intelligence itself, what if our own minds, what if we human beings think by computation? That's pretty hard to think that we are all just machines, but it's something philosophic and complex, and we at least we cannot answer it right now. And there is also another problem, because Professor Searle said that his Chinese room experiment can only apply to digital computers, but we know that there are several other kinds of computers developing, including quantum computers, biologic computers, and so even if we can't achieve strong AIs on digital computers, what about these other computers based on all new concepts? We don't know, but like in any field, we will always try to make it come true. And the next slide, please. Yeah, and that's all of my presentation, and thanks to these people, to my teacher, and yeah, and that's all. Thank you.
This issue for, I think, a number of hours, but we are going out of time, so I propose we can leave the remaining side presentation to next lecture, and we can finish here. So thank you again to everybody, and get prepared for yet another great lecture next week. Goodbye. Thank you.